Steel is a vital material in our everyday lives, supporting infrastructure, forming vehicles, tools, appliances, and more. But behind every beam, rail, or pipe lies a complex industrial journey that begins with iron ore. Transforming raw ore into strong, versatile steel requires several interconnected processes, each designed to extract, purify, and shape the material into its final form. The steel-making process begins with the production of coke, a carbon-rich material derived from black coal. In a facility called a coke oven battery, pulverized coal is heated to around 1,100 degrees Celsius in the absence of oxygen for about 24 hours. This heating drives off volatile components, leaving behind a gray-silver, porous, and highly combustible solid coke. Coke plays a dual role in steel production. It acts as a fuel and as a reducing agent in the blast furnace, enabling the extraction of pure iron from ore. Additionally, a byproduct of this process, raw coke oven gas, is captured and further processed for chemical use. The ore sintering plant, also known as the sintering unit, plays a critical role in preparing iron ore for the blast furnace. Here, fine iron ore dust, coke breeze, a byproduct of coke production, limestone, and other additives are blended with water to form a mixture called the sinter feed. This mixture is loaded onto a moving grate sintering belt, ignited at the top, and air is drawn downward to heat and partially melt the material. The result is sinter, strong, porous clumps that improve furnace permeability and fuel efficiency. The blast furnace is a massive, vertical structure used to extract molten iron from iron ore through a process called reduction. It operates continuously at temperatures reaching up to 2,300 degrees Celsius and is charged from the top with alternating layers of sinter, coke, and fluxes, such as limestone. As hot air is blown into the furnace from the bottom, combustion of coke generates intense heat and produces carbon monoxide, CO, the key reducing agent. In the upper cooler zones of the furnace, a series of indirect reduction reactions occur as CO gas rises and reacts with descending iron oxides. The process begins with hematite, iron 3 oxide, being reduced to magnetite, MuLTIVA-LENTFe3O4, then to wüstite, iron 2 oxide, and finally to metallic iron. The additional reaction, carbon dioxide plus C right pointing arrow to Colorado, plays a crucial role in maintaining the reducing environment within the blast furnace. As carbon dioxide is produced during the reduction of iron oxides, it descends into the hotter zones of the furnace, where it reacts with solid coke, carbon, to regenerate carbon monoxide, CO. This regenerated CO rises again, continuing the reduction cycle and enhancing the furnace's thermal and chemical efficiency. The steelmaking process begins in the steel plant, where molten pig iron from the blast furnace is refined into steel. Pig iron contains a high percentage of carbon, up to 5%, which makes it hard and brittle, unsuitable for most applications. To convert it into steel, the excess carbon and other impurities must be removed through a process called oxidation. This occurs in a converter, such as a basic oxygen furnace, BOF, or tandem furnace, where pure oxygen is blown at high pressure into the molten iron. The oxygen reacts violently with the carbon in the iron, generating heat and initiating the following oxidation reactions. 2C plus O right pointing arrow to Colorado, 2 Colorado plus O right pointing arrow to carbon dioxide. These reactions not only remove carbon by forming carbon monoxide and carbon dioxide gases which escape from the molten metal, but also help maintain the necessary temperature for the refining process without addition. As the carbon level decreases, the molten iron transforms into steel, a much more versatile and workable material. This controlled oxidation also removes other impurities like silicon, phosphorus, and manganese. The result is a more refined product, ready for further alloying and shaping according to specific industrial needs. Hot-rolled heavy plates are thick, flat steel products commonly used in construction, shipbuilding, pressure vessels, and industrial machinery. These plates are produced through a hot rolling process, where steel slabs are heated to high temperatures, typically above 1,700 degrees Fahrenheit, 927 degrees Celsius, and then rolled into desired thicknesses. The result is a plate with improved ductility and workability, suitable for heavy-duty applications. One of the primary advantages of hot-rolled heavy plates is their excellent mechanical properties. The high-temperature process refines the grain structure of the steel, enhancing its toughness and resistance to impact. While the surface finish is typically rougher than that of cold-rolled steel, hot-rolled plates are more cost-effective and easier to form and weld, making them ideal for large structural components. These plates come in a range of grades and thicknesses, often customized to meet the requirements of specific projects or standards, such as ASTM, EN, or JIS. They may be further processed through cutting, welding, or heat treatment to enhance performance characteristics like strength, corrosion resistance, or hardness. Sheet piles are long, interlocking steel, vinyl, or concrete sections driven into the ground to form continuous barriers for earth or water retention. They are widely used in construction and civil engineering for applications like retaining walls, seawalls, cofferdams, and flood protection systems. The primary function of sheet piles is to provide structural support and prevent soil or water movement. Steel sheet piles are the most common due to their high strength, durability, and ease of installation and removal. They are driven into the ground using vibratory hammers or pressing machines, forming a tight interlocking system that creates a rigid wall. The design and type of sheet pile used depend on soil conditions, load requirements, and the intended lifespan of the structure. One of the key advantages of sheet piles is their efficiency in space-constrained areas. Since they require minimal excavation, they are ideal for urban construction or marine environments where excavation is difficult or disruptive. Scrap steel is loaded into an electric arc furnace, where intense heat generated by high-voltage electrodes melts the material. Once molten, the steel is refined and poured into a continuous casting system, forming beam or slab-shaped billets. These are then reheated in a walking beam furnace for subsequent rolling into girders. The rolling mill breakdown stand reduces the reheated steel billets to the desired cross-sectional shape. Through a series of compressive passes, the girder's dimensions and mechanical properties are precisely controlled. Once the girders are formed, they are cut to the specified single lengths as per the project requirements. The material is then loaded into a sawing and drilling unit, where it is cut to precise, fixed lengths. Next, holes are drilled into the girders for spacers and lateral movement, ensuring proper alignment during installation. To prepare the steel for coating, the girders undergo shot blasting, a process that cleans the surface to a high standard, SA 2.5, removing impurities and rust. The girders are coated using thermal spray galvanization, where molten zinc is sprayed onto the surface to provide long-lasting corrosion protection. Before spraying, the flange areas are carefully masked to prevent coating in specified zones. After galvanizing, a primer coating with a thickness of 80 micrometers is uniformly applied to enhance durability and ensure strong adhesion for any additional protective layers. Upon arrival at the construction site, the girders are carefully unloaded using cranes or lifting equipment to avoid damage. They are then positioned onto a pre-assembled sliding frame, which allows for precise alignment. Once all girders are securely placed, the entire superstructure is gradually slid into its final position using hydraulic jacks or winch systems, ensuring accurate and stable installation. Roll bending is a metal forming process used to create curved shapes by passing a flat plate or sheet through a series of rolls. The process involves applying controlled pressure to gradually bend the material into cylindrical, conical, or spherical shapes. In roll bending, the material passes between at least two rolls, with one roll typically applying force, while others maintain the curve's alignment. The number of rolls and their configuration, such as in 3-roll or 4-roll machines, depends on the desired shape and the material's thickness. Roll bending is highly efficient for large-scale bending of plates and sections, and it can be used for both thick and thin materials. The technique is essential in industries such as shipbuilding, aerospace, and heavy manufacturing, where precise curvature is required for components like pipes, tanks, and structural sections. The process ensures high accuracy and minimal material distortion, making it an ideal choice for producing curved shapes in a wide range of applications. Tack welding is a preliminary welding process used to temporarily hold metal components in place before full welding is performed. It involves creating small welds called tack welds at strategic points along a joint to maintain alignment and prevent movement due to thermal distortion during final welding. Tack welds ensure accurate positioning, making the final welding process more efficient and precise. This method is especially useful in assembling large structures such as tanks, pipes, and frames, where maintaining dimensional accuracy is critical. Internal welding refers to the process of welding the inner surfaces of cylindrical or tubular structures, such as pipes, pressure vessels, or tanks. It is crucial for ensuring the structural integrity and leak-proof performance of components that will carry fluids or gases under pressure. Specialized equipment, such as internal welding heads or automatic orbital welding systems, is often used due to the confined space and precision required. Internal welding is common in industries like oil and gas, petrochemical, and pipeline construction. The process typically follows roll bending and tack welding, completing the internal seam before external welding is applied. The RIBO series is equipped with an advanced energy-saving drive system that optimizes power usage based on real-time load demands. This intelligent system minimizes energy waste during idle phases and adjusts motor speed dynamically to ensure only the necessary power is used during forming operations. The result is significantly lower operating costs, reduced heat generation, and enhanced overall machine efficiency without compromising performance. The fully automatic CNC playback control allows operators to record and replicate flanging cycles with precision, ensuring consistent results, reduced setup time, and minimal operator intervention for high-volume, repeatable production. The RIBO series delivers extremely smooth surface finishing through precise control of forming parameters and high-quality roll materials. This minimizes surface defects, reducing the need for additional polishing or machining. The result is a flawless finish that meets the highest industry standards, ideal for applications requiring aesthetic or hygienic surfaces. The RIBO series features a chamfering device with fully programmable position and speed, allowing for precise edge shaping tailored to specific dished end requirements. Operators can easily set and adjust parameters through the CNC interface, ensuring accurate, repeatable chamfering regardless of material thickness or head dimensions. This flexibility enhances productivity, reduces manual adjustments, and ensures consistent edge quality. By optimizing chamfering performance, the system contributes to smoother assembly processes and superior weld preparation, particularly important in pressure vessel and high-specification applications. The RIBO series is designed for efficiency, featuring an easy finished head removal system that minimizes handling time and risk of damage. Additionally, the quick knuckle roll replacement mechanism allows fast, tool-assisted changeovers, reducing downtime and increasing productivity during batch changes or maintenance, without compromising alignment or forming precision. The repair of a 15-ton press cylinder is a highly intricate and time-sensitive process, requiring precision and expertise. The first step involves the careful removal of the cylinder from the press. This is a delicate procedure to ensure that no damage occurs to the equipment or the surrounding machinery. Once removed, the cylinder is transported to the designated facility for further inspection and repair. In this case, the cylinder was delivered to Oberhausen at precisely 2:30 a.m., allowing for immediate attention once it arrived. Upon arrival, the team conducted a thorough inspection to assess the extent of the damage. The components of the cylinder were carefully examined for wear and tear, ensuring that every part was in optimal condition for regeneration. After the inspection, the regeneration process begins. This involves restoring the cylinder and its components to their original working condition, addressing any issues such as leaks, worn-out seals, or damaged internal parts. Once the regeneration is complete, the assembly process starts, followed by extensive testing to ensure that the cylinder performs as expected. Remarkably, the entire process, including disassembly, inspection, regeneration, assembly, and testing, was completed in just 3 working days. The Roundo angle roll R13S is designed for high-performance bending of large, heavy-duty profiles like the HEA 650. With its robust construction and precision engineering, it offers exceptional reliability and accuracy. The machine's advanced hydraulic system ensures smooth and controlled movements, while its infinitely variable speed allows for efficient bending of various profiles. The R13S is equipped with the innovative ROUNDO WCNC4 system, which provides a profile library, automatic bending cycle calculation, and the ability to store unlimited programs. The machine also includes automatic interpolation axis, ensuring multi-radius shapes are formed seamlessly on the same profile. This makes it ideal for bending standard or high-resistance profiles, such as beams, columns, and channels, with high efficiency and minimal operator intervention. The Roundo Angle Roll R13S is a powerful and versatile tool for those needing precision and flexibility in bending heavy-duty materials. The manufacturing process of couplings for rail vehicles at MSV Metal Studenka involves several key steps to ensure high-quality and durable components for both freight and passenger rail vehicles. The process begins with the selection of high-grade steel, which is then shaped and processed using advanced forging and machining techniques. The raw materials are heated to specific temperatures before being forged into coupling components. Precision machining follows, where the parts are further shaped, drilled, and threaded to meet the exact specifications required for different rail systems, including those for SBB Switzerland and DB Germany. Heat treatment processes like tempering and quenching enhance the strength and durability of the couplings. Finally, the couplings undergo rigorous quality control tests, such as non-destructive testing, to ensure their reliability and performance under harsh operating conditions. The CAD design process in the Siemens SBA compact system involves importing 3D models, typically in DSTV or IFC format, directly from structural detailing software. These models define the exact positions, dimensions, and orientation of all components. The system automatically interprets this data to plan the placement of parts, welding sequences, and tool paths, enabling fully automated, precise, and efficient fabrication. ADD parts are manually or robotically loaded into the system, positioned accurately for automated scanning, handling, and subsequent assembly. The system uses advanced 3D laser scanning or vision sensors to identify the exact shape, position, and orientation of ADD parts. This ensures precise alignment with the CAD model, enabling accurate robotic handling, positioning, and assembly with minimal manual intervention. The main beam, such as an H-beam or SIN beam, is loaded into the SBA compact system either manually or via automated conveyors. Precise positioning is ensured through sensors and alignment systems, preparing the beam for accurate part placement and welding. During assembly, the robotic system precisely positions ADD parts, such as cleats, stiffeners, and end plates, onto the main beam based on CAD data. Using multi-axis robotic arms and intelligent gripping systems, each part is accurately aligned and held in place. This process ensures consistent spacing, orientation, and contact, forming a high-quality assembly that's ready for automated welding without manual adjustments. The Auto Tool Change feature in the Siemens SBA Compact allows the robotic arm to automatically switch between various tools, such as grippers, clamps, and welding torches, without manual intervention. This system uses a docking station where tools are stored and exchanged as needed, based on the current task. Tool changes are triggered by the CAD program's instructions, ensuring optimal tool selection for each operation. This enhances efficiency, reduces downtime, and enables continuous multi-step processes within a single automated workflow. The auto-turning of ADD parts function enables the robotic system to automatically rotate or reorient connection parts, such as angles, cleats, end plates, and stiffeners, to match the precise installation angle defined in the CAD model. Once the parts are scanned and identified, the robot calculates the optimal turning path and uses a specially designed gripping tool to securely hold and manipulate the part. This eliminates the need for manual repositioning and ensures each part is presented to the beam in the correct orientation for welding. The system can handle a wide range of part geometries and weights, maintaining alignment tolerances within millimeters. Auto-turning significantly increases accuracy, reduces handling time, and supports fully autonomous assembly, even with complex geometries and custom fabricated components. The Z-Man SBA Compact is engineered to handle both standard welded beams and SIN beams as primary structural members. Welded beams, typically fabricated from flat plates welded together to form I or H profiles, offer design flexibility and high load-bearing capacity. The system accommodates these by accurately aligning and assembling ADD parts along their flanges and webs using CAD-driven precision. Additionally, the SBA Compact is optimized for SIN beams, innovative beams, featuring sinusoidal web profiles that reduce weight while maintaining strength. These beams require specialized handling due to their curved geometry. The robotic system automatically compensates for the sinusoidal shape, ensuring ADD parts are correctly positioned and welded without distortion. This capability allows fabricators to process a wider variety of beam types with a single, automated solution, improving productivity and supporting lightweight, cost-effective construction methods in steel fabrication. Preheating is applied to the beam or ADD parts before welding, especially for thick or high-strength steel. Using induction or gas heating methods, it reduces thermal stress, minimizes cracking risk, and ensures better weld penetration and overall joint integrity.